Good day, everyone. So we are reviewing Wetzel's Limnology textbook. This is edition number 4. We're on chapter 14, which deals with the inorganic carbon complex. And today we'll be starting with carbon dioxide exchange between the atmosphere and water. Where the partial pressure of CO2 in water does not equal the partial pressure of CO2 in the atmosphere, there will be a net flux of CO2 from air to water, or vice versa. We can estimate the magnitude of this flux and then use that to obtain important insight as to how carbon is cycled in inland waters. To do this, we need to consider the physics of gas diffusion at the air-water interface. A diffusive flux is proportional to the concentration, in this case the partial pressure, gradient, existing at the interface. It can be described by a simple equation of the flux is equal to K by KH, by the subtraction of PCO2 in the atmosphere from the PCO2 in water. KH is the temperature-dependent Henry's constant in equation 13-2. KH by PCO2 gives the concentration of CO2 in water in micromoles per liter. Similarly, KH by PCO2 in the atmosphere gives the concentration the water would have had it been in equilibrium with the atmosphere. This equation can be rewritten as flux is equal to K by CO2 concentration in water minus CO2 concentration at equilibrium, where K is the gas exchange velocity, often termed piston velocity. In this equation, the concentration of CO2 in equilibrium means the concentration the water would have had it been in equilibrium with the atmosphere. The piston velocity is a way to represent the physical rate of gas exchange with the atmosphere. The variable K can be thought too of as the height of water that exchange gas per unit time with the atmosphere, as if a piston pushed the excess CO2, for example in the case of oversaturation, through that height of water. The value of K is the result of turbulent energy exchange with the atmosphere and increases with factors such as wind and current speed. Embedded in K is a diffusion constant for a given gas. Thus, K is a specific value for a given gas. At a given value of K for one gas and temperature, it can be calculated for any other gas and temperature by using the Schmidt number SC equation from Yarney et al. So K gas 1 divided by K gas 2 is equal to SC gas 1 divided by SC gas 2 to the power of n, where n can vary from unity to minus 0.67. Minus 0.5 is a commonly assumed value for n. Vanikoff provides a useful table that gives equation to calculate the SC number for several gases at any temperature. For CO2, the equation is 1911.1 minus 118.1 by T plus 3.4527 by T to the square minus 0.04132 by T to the cube, where T is temperature in degrees Celsius. The SC number for CO2 at 20 degrees C is 600. When K is measured, it is usually expressed as K600, meaning that the K value for a gas and temperature combination that equals 600 in Schmidt number. While not straightforward to do, K can be measured directly. These approaches include adding an inert gas tracer such as SF6 using floating chambers, but correcting for chamber effects on turbulence, modeling short-term changes in the temperature profile, and employing more complex statistical methods using either multiple isotopes of a gas or multiple different gases. Where they have been compared, these approaches agree reasonably well. From the measurement of K along with other factors, we know that K is greatly affected by factors affecting the turbulent regime of surface waters such as wind, current speed, and convection, while several other factors are known to influence gas exchange velocities. The most widely used models predict K from wind speed in lakes, from wind and current in large rivers, and current and water depth and slope in shallow rivers. In a lake with low winds, K would be near 0.4 meters per day, about 1 to 3 meters per day in a windy lake or turbulent but deep river. Higher, greater than 10 meters per day, in shallow streams running over rocks, and extremely high in alpine streams, much greater than 100 meters per day. In small streams, researchers often model K as a linear distance or reaeration length or time, rather than as a piston velocity. There are a number of useful empirical relationships by which one can predict K from wind, current speed, and other easy-to-measure features of a given system. If we express K in meters per day and realize that CO2 in micromoles per liter is the same as millimoles per meter cube, flux in equation 13-17 has the useful units of millimoles of CO2 per meter squared per day. When CO2 water is greater than CO2 atmosphere, the flux is from the water to the air, and the water body is the source of CO2 to the atmosphere. The opposite is true when CO2 water is less than CO2 atmosphere. Chemically enhanced diffusion. At very low CO2 concentrations and concomitantly very high pH, CO2 exchange with the atmosphere is controlled in part by factors other than regular diffusions. What we know is that under these conditions, CO2 enters the water much faster, 7 to 20 times faster, than can be explained by the diffusion equations above. This is called chemically enhanced diffusion. The kinetic and isotopic evidence suggests that CO2 from the air reacts directly with the hydroxyl ion in the surface water more quickly than it can diffuse across the air-water interface, forming bicarbonate. So CO2 concentration plus hydroxide concentration is equal to bicarbonate concentration. We express this chemical enhancement as beta. The enhancement factor, which is simply the ratio of measured K under enhanced conditions, K, E, A, E, and H, to what K would be without the enhancement. Bad and Cole found reasonable agreement between measurements of CO2 flux using floating chambers and models of K, E, and H using Wanikoff and Knox, etc., to predict beta. In the studied low wind lake, beta ranged from 3-fold to 6-fold increased with increasing pH and has strong effects on the isotopic fractionation of the CO2 that was exchanged. Using a time series modeling approach on the concentration of carbon-13 DIC in the surface water, the use of beta caused closer agreement with measured carbon-13 DIC than without chemical enhancement. As discussed later in this chapter, CO2 from the respiratory processes of decomposition can also accumulate to large quantities in the hypolimnia of lakes. Spatial and temporal distribution of total inorganic carbon and pH in rivers and lakes, rivers and streams. In many streams and rivers, decomposition dominates over in-channel photosynthetic production, leading to the production of CO2 being higher than its consumption by photosynthesis. In addition, inflowing water from runoff of soils of both surface and groundwater sources would typically have large concentration of CO2 from bacterial and plant root respiration. Carbon dioxide in high concentration above equilibrium values is relatively rapidly lost to the atmosphere, particularly in the water turbulence of streams. Respiration within the streams and river water is high, however, and CO2 production can exceed evasive losses to the atmosphere and photosynthetic utilization. For example, several Danish streams contain about 8 times more free CO2, PCO2 is equal to the 10 to the minus 2.6 atmosphere, than water in equilibrium with air, where the partial pressure of CO2 is equal to 10 to the minus 3.5 atmosphere. As a result, variation in the CO2 concentrations are common. Higher concentration and reduced pH can be found in quiescent regions or times of reduced flows, particularly near wetland areas of high loadings of dissolved and particulate organic matters. Changes in alkalinity and pH can also be induced by rapid changes in discharge. For example, alkalinity depressions in streams water can result from dilution by snowmelt water, although discharge was positively correlated with alkalinity in circumneutral streams. In acidic streams with little buffering capacity, the snowmelt can induce marked short-term reduction in pH and create conditions that can be lethal to certain biota. In hard water bicarbonate rivers such as the Rhine and the Rhone rivers, total CO2 largely as bicarbonate increased downstreams from the source, mostly as a result of increased organic loading and decomposition. Seasonality was evident in both the bicarbonate concentration and pH, largely as a result of temperature on the solubility of CO2. Upon entering reservoirs, many of the features discussed later for lakes apply. However, the complexities of reservoirs, morphometry, inflow volumes, and density-mediated distributions, as well as retention times, make generalizations difficult. DIC in stratified lakes. DIC in stratified lakes shows a number of interesting features. During periods of mixing, DIC is distributed near uniformly with depth in typical dimictic and monomictic lakes, and in shallow lakes of insufficient depth for thermal stratification. The DIC content of the water is dependent upon the equilibria established between atmospheric CO2, the bicarbonate-carbonate system, external loadings, contributions from metabolic respiration, and utilization in photosynthesis. Metabolism is markedly influenced by numerous parameters. In the spring, increasing light and temperature exert major controls on the photosynthetic uptake of CO2, and generation rates of CO2 from microbial decomposition of organic matter are temperature and oxygen dependent. Vertical distribution of DIC. During the period of thermal stratification, several conspicuous changes occur in the vertical distribution of DIC, largely due to the changing balance between primary production, which requires light, and respiration, which does not. Below the upper mixed, DIC usually increases and mirrors the degree in dissolved oxygen. In deep oligotrophic lakes, these increases in DIC are usually not very large and are limited by the low supply of organic matter from the trophogenic zone. In shallow or more eutrophic lakes, where the supply of organic carbon is larger, or if the mixing is less frequent, oxygen can be completely consumed with a concomitant increase in dissolved CO2 and DIC. In systems where there is sufficient supply of alternative electron acceptors such as nitrate, sulfate, or iron, anaerobic respiration becomes dominant in the hypolimnion, and the DIC increase as CO2 but also as bicarbonate can be very large indeed. For example, in Siders Pond, a coastal pond near Woods Hole, Massachusetts, DIC increased from about 841 micromoles per liter at the surface to 12,236 micromoles per liter at the 13 meters depth. 30 meters depth is about 30 feet. This system, which is probably meromictic and usually anoxic below about 5 meters, has very high sulfate concentrations, 3,500 micromoles per liter. In surface water, because it is brackish, that amount of sulfate could generate 14,000 micromoles of liter of DIC per liter of DIC if all the sulfates were used in sulfate reduction. So the observed 11,393 micromoles per liter increase in DIC can potentially be accounted for by sulfate reduction alone in the system. Even in lakes with relatively low sulfate, DIC can build up to high levels through multiple processes. Black Pond in the White Mountains of New Hampshire was also in the Caraco et al. Dataset. This lake has about 50 micromoles per liter sulfate in surface water. The lake is mesotrophic, well stratified, and anoxic in the hypolimnion. Black Pond is oligomictic and builds up about 1,400 micromoles per liter. DIC above the surface values, in Black Pond, both CO2 and DIC concentrations are much higher than can be accounted for by aerobic decomposition alone. Also, much of the DIC accumulation is as bicarbonate, unlike the case in Lake Lacroche, where it was all in the form of CO2. In the bottom waters of Black Pond, then, one or more of the alkalinity-generating oxidation pathways must dominate. Some of the CO2 in Black Pond came from acetoclastic methanogenesis, as bottom water methane, CH4, reached over 600 micromoles per liter. Sulfate reduction could add at most 80 micromoles per liter. DIC as ANC, and iron reductions perhaps another 100 micromole. In every case in which water is oxic, we can completely account for the increase in CO2 from oxic decomposition. However, in the anoxic waters, we are missing major processes that generated more than half of the observed increase in bicarbonate. This is more inorganic carbon, that is, more inorganic carbon is generated than we can account for by measured electron acceptors in the water column. The remainder might come from manganese reduction or some ionic exchange within the sediment, or with the sediment. So let's look at this figure here, figure 13-6, depth profile of partial pressure of CO2 in Lake Lacroche. The time series of the increase of hypolimnetic CO2 can be used to calculate hypolimnetic CO2 accumulation. For lakes with significant amount of anaerobic respiration, one would need to use DIC instead of CO2 because of the generation of ANC during those processes. So y-axis we have the depth in meters, and the x-axis we have the concentration of CO2 in micromoles per liter, and then we have color codes depending on the month. So we have May, where we have, like an increase of CO2, and then there's a decrease of CO2 right at, I'm assuming, at the time that we are reaching the sediment. June looks like it likes the same pattern up to 6 meters depth, but then we have higher concentration, which is going to be the trend for up to September of CO2. So CO2 is increasing in the hypolimnion, as we can see, and we can detect that July probably see the highest increase of CO2 in terms of rate than the other months. So the Lake Mendota is a hard water eutrophic lake that is typically dimictic. In this lake, we again see that the increase in CO2 is balanced by the decrease in oxygen in the oxic zone, and below this, both DIC and ANC increase. While sulfate is moderately high, about 100 micromoles per liter, it is insufficient to explain the large increase in DIC in the anoxic water, even if all the sulfates were reduced. We need to assume again that other unmeasured electron acceptors were involved. In studies that have tried to explain all of the electron acceptors in anaerobic waters, it is often the case that we come up with an electron acceptor deficit. That is, there is more DIC accumulation than we can account for by the measured electron acceptors. The vertical distribution of total DIC and pH are strongly influenced by various biologically mediated redox reactions. Most conspicuous is the photosynthetic utilization of DIC in the trophogenic zone, which tends to reduce CO2 content and to increase pH, and the respiratory generation of CO2 throughout the water column and sediment, which tends to decrease pH. In addition to the heterotrophic degradation of organic matter, the generation of CO2 and reduction of pH are augmented by microbial methane fermentation, nitrification of ammonia, and sulfate oxidation. Further, denitrification of nitrate to molecular nitrogen, reduction of sulfate to sulfite, and iron and manganese reduction can result in a net increase in pH and alkalinity. The combination of the decompositional processes results in an increase in the DIC of the hypolimnetic waters and a decrease in pH compared to that in surface waters. And that will be it for today. We'll pick it up tomorrow with as the intensity of decomposition increase in the tropholithic zone. So I appreciate your attendance today, and I look forward to seeing you tomorrow. And thank you for attending this review of Limnology with me, and I'll talk to you tomorrow. Thank you. Bye.